Welcome everyone. In this video I will show you another way of measuring temperature. So in my previous videos I showed you I think at least 3 different kind of measurement techniques. This was, for example, a K-type thermocouple or a digital chip or an analog chip. So 2 of these measurement techniques were based on some kind of semiconductor, and the third one was based on the thermoelectric effect, where you join 2 different metals and that generates some voltage, thermoelectric voltage, and by measuring this thermoelectric voltage you can get the temperature. And now I show you a third principle or a fourth thermometer, and this is the NTC thermistor. So what does that mean? That means that when you change the temperature of it, you increase the temperature of the device, then the device will show you negative or decreasing resistance. So essentially this thing is a resistor. As you can see it here, it's a very tiny blob. It's an epoxy shielding or protective thing, and inside there is a resistor. And when you expose this to temperature changes, as I said, when you increase the temperature of this blob, then the resistance of this thing will decrease, and when you decrease the temperature of this, then the resistance of this unit will increase. And this is a very nice measurement technique because it's very simple and it's very convenient to use. And for today's demonstration I will use an STM32 circuit or blue pill, a voltage divider where one of the element is a thermistor, and an LCD display, just to show you the results. And since I will use this in some other application, I will also show you some applications. And then in a following video or an upcoming video, I will show you some other applications of this thing. But why is this so popular, or why is it so good to use? So it's tiny, so you can use it in several different places where you have a limited amount of space available. And it is also cheap. It's very cheap. I don't remember the exact price, but you can buy a handful of this for just a couple of dollars. But what is important is that you can buy it in this format. So as you can see, it's pre-made, and you can see that here there is a nice sealing of the cable, and you can see that it also has a connector. And if you cannot guess, I can tell you that this particular unit is used in the hot end of a 3D printer. So now I can actually demonstrate you one of the application areas, which is the 3D printers. So basically this guy gives a feedback to the 3D printers electronics, and by that you can, or the microprocessor can regulate the temperature of the hot end. And then another application which will be more interesting for us in the future is this. So this is a plug with this, I think, G1/4 thread, where in the end of this plug we have the same thermistor as I have it in the breadboard. And what is nice about this is that when you are using these water cooler things, the thread is matching. So I can in fact just plug it here, and now I'm able to measure the temperature of the water which passes through this 3-way flow indicator. And actually I will use this in an upcoming video, so that's why I want to show you this circuit, so you will have some knowledge about this thing here. And some other details about this thing is that these are usually come in 10 kilo ohms format or value, which means that at 25 degrees room temperature this value is around 10 kilo ohms, and we can actually measure it. Now I touched it, so it will be maybe a bit different, but let me put this thing here so you see it. And then approximately 10 kilo ohms should be shown. So now as I touched it, I warmed up this place or this area of the thermistor, so I decreased the resistance. But now, as you can see, it's cooling down, so the resistance of the thing increases. So I touch it again just to show you. And you can see that basically from 25 degrees to 35 degrees, you have a quite significant change in the temperature. And then how you measure it is very simple. I will put this thing, the circuit schematics, on my website. So don't forget to check the description of this video, and then you will find the link for the drawing. But what happens here is very, very simple. So that's why I like this kind of circuit. We built a voltage divider here, and what I did, I used the same value resistor as the R1, so the first resistor in the divider. So I have a 10 kilo ohm resistor here, and we have a 10 kilo ohm thermistor here. And in the middle, we measure the voltage with the A0 pin of this STM32. And I will show you the circuit on my computer, and I will also show you the whole code. But once again, check the description before asking for the source code, because the source code is available, as always, in the description, as well as the drawing of this very, very simple circuit. So basically what we have, the display is connected to the microcontroller, to the SDA and SCL pins, and then this is connected to the 5 volt rail. And you should know that the STM32 prefers 3.3 volt, so we are using 3.3 volt in the voltage divider as the supply voltage, and then we measure that. And I will tell you some information about the AD conversion in the STM32, because that's a bit different, or I mean there are some different practices which should be kept in mind, but it's basically the same as the Arduino. So I also want to emphasize that you can just replace this microcontroller to a regular Arduino Nano or Uno, and you can use it in the same way. You just have to use different pins for the display and perhaps a bit different coding, but I will provide both codes, or I just put there a comment to those places where you have to modify the code in order to be able to run it in Arduino. But yeah, we have this voltage divider, and we just measure the output voltage. So I just connect my power supply, and you should see the screen. So we have just some startup text, and then we have the temperature. So according to this now, I print the temperature in Kelvin degrees and Celsius degrees. So we are pretty much at 25 degrees. And we can ask our friend, the K-type thermocouple, if this is true. So this should show roughly the same temperature. So you can see that 24.8 and 24.8 pretty much. And now I try to squeeze them together with my fingers and show you that they are roughly measuring the same. So you can see both of them are showing like 35 degrees more or less, and that's pretty much close. So basically this is all. I just wanted to show you the basic principles of this circuit, and now I will go to the computer and show you more details, first about the circuit and then about the code. So let's go to the computer and talk about this circuit in more details. So let's start with the schematics, and you can see that we basically have 4 components. The LCD here, the STM32, which can be exchanged to an Arduino, of course, and then we have a resistor here in the voltage divider, and we have the thermistor in the second part of the voltage divider. So let's just check the connections for the LCD. So you can see that this works with the I2C standard. So we are using the SDA and SCL pins, and in the case of this blue pill, it's the B6 for the SDA and B7 for the SCL. And if you want to see it for Arduino, then we have the SDA at the A4 pin, and we have the SCL in the A5 pin. So this is what you have to change if you go to Arduino Nano or Uno, for example. Then these are the SDA and SCL pins, but you can always look it up on Google. And then this is using 5 volt, so we are using plus 5 volt rail from the STM32, and of course we have the GND connection here and nothing else. That's very simple. And then basically this part is the voltage divider, and I wrote a few details here. So one thing which you have to keep in mind is very important, that opposite to the Arduino, the STM32 uses 3.3 volt as the reference of the ADC, which means that you have to use the 3.3 volts when you convert the bits into voltage. And that's important, because if you miss it, then you get weird values. Another important thing is that Arduino has, again, I write it down. So the Arduino has only 10 bits of resolutions, which means that we have 1024 different values. So basically from 0 to 1023. And then we have the blue pill or STM32, which has 12 bits. So that means that we have 4096 different bits, and that goes from 0 to 4095. So this is very important, because if you see that in this case we divide the 5 volt into 1024 parts, but here, since the reference is 3.3 volts, we divide that into 4096 parts. So if you see that the resolution is quite different, because here we use larger voltage and less amount of steps, and here we have lower voltage and more steps, 4 times more steps. So here you can get better resolution, so the difference between 2 bits will be smaller in voltage. So this is good to know if you are using STM32. So here we feed 3.3 volts to the voltage divider, so I just write it down here as well. So this is the input, and in fact you can feed the 5 volt, but it's not a good idea. And first of all, why I say this is because if you cool down the NTC too much, it might happen that you get more than 3.3 volt at the input of the ADC here, and this pin is not 5 volt tolerant. Most of the pins are 5 volt tolerant pins, but the ADC pins are not, so they can accept maximum 3.3 volts. So this is one safety step. But if you for some reason still want to use the 5 volt rail, you just have to make sure that you use a higher R1, and then you have to do the calculation. So we start to work with the voltage divider. We know that the input is 3.3 volt, and then the R1, which is this value here, or this resistor here, has a 10 kilo ohm resistance. And why I choose this to be the same as the R2, which is also a 10K thermistor at 25 degrees, it's very important. Then we know that if these values are identical in the voltage divider, then the output here will be the half of the supply voltage, so half of the 3.3 volts. So 1.65 volt will appear here if we are at room temperature, and these values are identical. And basically this is all. So we use this simple voltage divider with identical components at 25 degrees, and we measure the output voltage. So the output voltage should be around 1.6 volts at room temperature. And when you start to, for example, increase the temperature here at the thermistor, which means that the resistance of this thing will decrease, then the V out, which is this guy here, so the output voltage which is measured at the A0 pin, is decreasing. So then the higher the temperature here, the lower the input voltage of the A0 pin. And then we use some formula to convert this voltage first into the value of this thermistor here. So we just rearrange the formula for the voltage divider, and then based on that resistance value we calculate the temperature. And basically that's all. But I will show you that in the part where I show the code of this microcontroller. So then basically this is all. It's a very simple circuit, but we can use it for many different things. And maybe the simplicity and also the fact that it is cheap makes it very good for use. So now we should go to the Arduino IDE and go through the code very quickly. So this is the code here, and let's go through the variables first. So we have a supply voltage, 3.3 volts. I measured it, and it is basically 3.3 exactly. So you can measure it and write the same value that you measured, but we can believe that 3.3 is 3.3. We have to define V out value, that is the output of the voltage divider, and then we have the resistance of the thermistor, and then we have to write the exact value of the 10K resistor here. So you take your multimeter, put it into resistance mode, and you should measure the exact resistance of the resistor that you want to use in the voltage divider, and don't put it in the circuit, remove it from the circuit and just measure it outside the circuit. So in my case this was 9840 ohms. And then this is a very important parameter. This is a so-called B coefficient for the thermistor. It is usually provided by the manufacturer if you buy the thermistor from a decent place. But then if you buy them in bulk or something, they are usually not defined or not published, I would say. So you should use somewhere between 3,700, 4,000, it depends on. But you can experiment with this. If you know, for example, a certain temperature very well, let's say water with ice, which should be 0 degrees Celsius, as long as you have ice in that bath, then you can calibrate your beta parameter to a value where you get 0 degrees Celsius when you measure that ice bath temperature. And then we have the T0, and we have to define it in Kelvin. So this is 25 degrees in Kelvin, because the formula which converts the resistance of the NTC into temperature is using Kelvin as the unit for the temperature. So we use that. And then we have two variables to define the temperature in Kelvin and Celsius. And then we define the PA0 pin as the input pin for the AD converter. And here, if you use STM32, you have to use PA0. But if you have Arduino, you just get rid of this, and then you use A0. But I'm working with STM32, so I have to use this. Then here we have a few time-related variables. This is just to measure the time in milliseconds at certain moments. And we define an update interval, which is half a second. So this will be used to update the LCD. So the LCD is updated twice in a second. So we just use the standard library for the LCD. So this is the 16:2 LCD. And then as I showed it in the circuit diagram, this is the SDA1 and SCL1 for the STM32, and there are two I2C connections, but we use the one. So this is PB7, PB6, and if you are using Arduino, then A4, A5 for SDA and SCL respectively. And then we go to the setup part. So we just start the serial, we start the LCD, and we just print something. We wait a little bit, and then we prepare the LCD with this print LCD function. So basically I replace this message with the temperature values. So that is what is shown here. So we clear the message, the startup message, and then we just put the cursor in the 0, 0, so first line and the first block, and print this, and then we move the cursor to the 10th block, so 9 plus 1, because we start counting from 0, and then we measure, or we print the temp K, and for the first, right after the startup, for the first time, this will be 0, of course, because this function haven't run yet. And we do the same with the second line. So with the second part of the argument of the setCursor function, you go to the second line, and this is number 1 because we start counting from 0. So the first line is 0 and the second line is 1. And then we just do the same exercise. So first the first block here, as you can see, and then here, as you can see, we jump to the 9 again, or 10, and then just print the value of the temperature in Celsius. So that's done, and we have to set this input as an analog input here. So we just define the Vout pin as the analog input, and then we start the timer. So we just simply say that the value of time now 1 is the current elapsed time in millis, and then we will refer to this later. So we go to the loop, and then we get the time again, and then we find the if condition here. So if the time difference between the time which was recently read just before the if and the time which was measured first in the setup, so this is right after starting the Arduino or STM32, is larger than the 500 millis, which is defined here, then we can enter and we update the LCD. And the update LCD is nothing else that we just go to the certain parts of this LCD, and then we just update the values of the numbers. So we don't touch these parts, this and this, which was printed in the very beginning, but we just touch these parts from the print LCD. So those values, so we set the cursor, actually we jump to the number 9. So let me fix this. And then we just print the numbers. So we just update the numbers, and at the same time, when the LCD is updated, we also send the value and some message through the terminal. So at least I can show it to you here. So I will show that in a few seconds. So when we update the LCD, first we print it on the LCD and also on the serial port. If you don't need this, it's very simple, you just comment it out. So now the LCD is updated, and then we jump to the convert to temperature function, and then here comes our formula. So first we determine the output voltage, and that is defined by this formula. So as I said, the reference voltage is 3.3 volts and not 5. If you are using Arduino, you have to update the part in the parentheses. I just write this down. So for Arduino users, the parentheses should look like something like this. So this part. So if you are watching this video and you are planning to replicate this project in an Arduino, you have to replace this part with this part, and that's all. So what happens here is that you get a value between 0 and 4095, and then you just multiply that value by this number, and you get the value in voltage. And as a checking, I print this to the terminal as well, so we can see the value of the voltage. And then by rearranging the voltage divider formula, we can get the value for the R2, which is the NTC resistor. So this is what is happening here. So V out times R10K, which is the R1, the resistor in the voltage divider, divided by the supply voltage, which is 3.3 for my circuit. But if you are using Arduino and you are planning to use it with the 5 volt, then you have to go back to the beginning of the code, and then you have to replace this to 5 volt. And V out is just measured up here. So then I just print this out to see what is the value. And then we come to this final formula, which is the temperature in Kelvin. So what happens is that there is an exponential correlation between the temperature and the resistance of the NTC. So then that formula is implemented here. And you can see that we are using this B parameter, which is 3700 in our case. And then the T0 is just the room temperature in Kelvin. And then we just do the rest here. And basically that's all. And after getting the temperature in Kelvin, we get the temperature in Celsius by subtracting 273.15. And that's all. So as you can see, this is very simple, and this was the whole code. Also, I just wrote some discussion and things here, so you will see this as well in the uploaded code. And basically that's all. So now I connect my circuit to the computer this time, and we will see what we can do with this. So now you see that this goes very quickly, so I just stop it. So now you can see that it is almost 10 kilo ohms, so we are at room temperature. As I said, since the values in the voltage divider are identical, we get half of the input voltage. So this is 3.3 divided by 2, and you can see that now I scroll it manually, but we pretty much get the same values all the time. So now I put the auto scroll in, and I touch the thermistor, and you can see that the value drops. So I stop it, just I can show it to you. So now you see that the output voltage dropped down from 1.66 to 1.38, and also the resistance changed and decreased since I touched it, and increased the temperature of this thermistor. So basically this is all. And now maybe this is not so exciting, but I will use this in many other projects which involve cooling and heating, and that will be more interesting. But I wanted to share the basic principles of this thing, so when you try to create a very simple thermometer, you can do it by following this video. So this was all. I hope you liked this video, and I hope you learned something. If you want the source code, or you want to have the schematics, please visit my website, curiousscientist.tech. You will see the link for the blog post in the description. Please don't forget to subscribe, and see you in the next video.